Hello and welcome. In this video, I'm going to discuss about Bayes theorem. This is a continuation of the video on conditional probability. To calculate the probability of A intersection B, for example, we can use the formula from conditional probability. If probability of A intersection B is not known, but probability of A and probability of B given A are known, we can use the multiplication rule for probabilities to calculate probability of A intersection B, which is probability of B given A times probability of A. And note that A and B are said to be exhaustive if their union is the sample space. Suppose we have an event B. We can partition the event B into two mutually exclusive subsets in such a way that if any set B has part in A and also part in A complement, as we know, A and A complement are mutually exclusive and also exhaustive because their union is the sample space, which is B. So B can be expressed as B intersection A union B intersection A complement. Then what will be probability of B? Probability of B will be probability of B intersection A plus probability of B intersection A complement, because A and A complement are mutually exclusive and exhaustive. From the multiplication rule for probabilities, we can calculate the probability of B intersection A as probability of B given A times probability of A, and the probability of B intersection A complement as probability of B given A complement times probability of A complement. From the total probability rule for two events, probability of B will be probability of B given A times probability of A plus probability of B given A complement times probability of A complement. Okay, what if we have multiple events? It means assume we have events E1, E2 up to EK, which are K mutually exclusive and exhaustive sets. And B is partitioned into these mutually exclusive and exhaustive events. So what will be probability of B? From the total probability rule, we can calculate probability of B as probability of B given E1 times probability of E1 plus probability of B given E2 times probability of E2 plus up to probability of B given EK times probability of EK. Okay, so this will help us to use Bayes theorem. How? As follows. Suppose probability of B is known, probability of A is known, probability of B given A is known, but probability of A given B is not known. So how do we calculate? From the conditional probability formula, probability of A given B will be probability of B intersection A divided by probability of B. And from the multiplication rule for probabilities, the numerator will be probability of B given A times probability of A, and the denominator will be probability of B, where probability of B is greater than 0. And so, if we have events E1, E2 up to EK, which are mutually exclusive and exhaustive events, and these events are the partitions of the event B, then what will be probability of E1 given B? And also similarly, what will be probability of E2 given B? And so on. So for general I, if this is I, we can put I here also I. What is probability of EI given P? It will be probability of B given EI times probability of EI divided by the summation of probability of B given EI times probability of EI. So for example, for one only, E1 is probability of E1 given B will be probability of B given E1 times probability of E1 divided by the summation of probability of B given EI times probability of EI. So that's how it works. So note that the numerator is always equals with one of the terms in the sum in the denominator. Now let's do some examples. The first example is about medical diagnostic. A medical screening of the population is proposed because a new diagnostic procedure is effective in the early detection of a rare disease or illness. The test has a prevalence of 0.0001, which is probability of D is 0.0001, and specificity of 0.95 and sensitivity of 0.99. If someone takes the test and the result is positive, what is the probability that they actually have the disease? These are the given ones. So what we are asked is to calculate the probability of D given P. And that is probability of P given D times probability of D divided by probability of P given D times probability of D plus probability of P given D complement times probability of D complement. From the given one, this is not given, but we know that probability of P given D complement plus probability of P complement given D complement is 1. And this is given, which is 0.95. And so this will be 0.05 in order to have 1. So what will be probability of D given P then? It will be 0.99 times 0.0001 divided by 0.99 times 0.0001 plus 0.05, which is this one, times 0.9999, which is 1 minus of this expression. And this expression is equals with 0.002. And you can also see it in here. So what does it mean? It means that even though the test is effective, the chances are quite small that you actually have the disease because the probability of D given P is very small, which is 0.002. We can also do it in R. This is a code, and how we can do in R is the following. So I can run this, run this, run this, run this, and I can use the Bayes theorem to calculate, and it is 0.001976 approximately, which is 0.002. Okay, now let's see the next example. Example 2 is about advertising. A company runs an online ad campaign and finds that only 5% of all visitors to its website buy. However, data shows that 80% of those who buy clicked on an ad, while only 10% of those who didn't buy clicked on an ad. if a visitor clicked on an ad, what is the probability that they actually buy? And these are the given ones. So for example 2, what we are asked is to find probability of B given that they click on the ad. And that is probability of click given by times probability of buy divided by probability of click given by times probability of buy plus probability of click given by complement times probability of by complement. Okay, from here, what is the given here is 0.8. And this one probability of B is 0.05 from the given ones divided by 0.8 times 0.05 plus 0.1 times 0.95. And that expression is 0.296. That we can also see it here. And so there is a 29.6% chance a clicking visitor will buy. We can also do it in R. This is a code. And how we can do is we can run probability of buy, which is 0.05, not buy, and click given by, click given not buy. And so using the Bayes theorem, we can have the probability of buy given click, which is 0.296, and we can interpret it as 29.6% chance a clicked visitor will buy. Okay, what about the next example? In the next example, which is hiring accuracy, it said, a company interviews candidates and uses a screening test. Suppose 30% of all applicants are truly qualified. The test correctly identifies 85% of qualified candidates, but also incorrectly passes 20% of the unqualified ones. If a candidate passes the test, what is the probability they are truly qualified? So the given ones are this. For example 3, we are asked to calculate probability of Q given test positive. That is calculated as probability of test positive given qualified times probability of qualified divided by probability of test positive given qualified times probability of qualified plus probability of test positive given not qualified times probability of not qualified. And that is, this one is 0.85 times, this is 0.3 divided by 0.85 times 0.3 plus 0.2 times 0.7. And that expression is 0.646. And we can also see this calculation here, which is 0.646. And we can say around 64.6% chance the candidate is truly qualified. We can also write in R using this code, and we can also see if the result is the same. So P qualified is 0.3, not qualified, test pass given qualified, test pass given not qualified, and then using Bayes theorem, we can calculate the probability of qualified given test pass to be 0.6455. Let's consider example 4. It's about manufacturing. A factory uses 2 machines. Machine A makes 60% of bulbs with a 2% defective rates. And machine B makes 40% of bulbs with a 5% defective rate. If a bulb is defective, what is the probability that it came from machine B? So these are the given ones. In example 4, we are asked to find probability of B given defective. And that is probability of defective given B times probability of B divided by probability of D given B times probability of B plus probability of D given B complement times probability of B complement. In this case, please note that B complement is A, I mean. So probability of B complement means probability of A, and probability of D given B complement means probability of D given A. So then substitute instead of this formula the given ones, which is 0.05 times 0.4 divided by 0.05 times 0.4 plus 0.02 times 0.6, and that expression is equal with 0.625, which is 62.5%. And that is about 62.5% chance it came from machine B. And this is the code for R. We can also see in R, this is probability of A, probability of B, probability of defective given A, defective given B. And then using the Bayes theorem, this is the formula. And so probability of B given defective is 0.625. Okay. What if we have another example? In example 5 is about Bayesian networks. Bayesian networks are used on the website of high technology manufacturers to allow customers to quickly diagnose problems with products. A printer manufacturer obtained the following probability from a database of test results. So we have probability of H 0.1, probability of S 0.6, and probability of O 0.3. And we can have also other given ones. So from these given ones, if a customer enters the manufacturer's website to diagnose a printer failure, what is the most likely cause of the problem? The most likely cause of the problem is the probability with a high value. So we are asked to find probability of H given F, probability of S given F, probability of O given F. And then we will say the highest probability is the most likely cause of the problem. And to calculate that, we need to calculate probability of F because probability of F is our denominator. So in example 5, we have probability of H, probability of S, we have probability of also other. We have probability of F given H, probability of F given S, probability of F given O. But we do not have probability of H given F. That is the question. Also probability of S given F, probability of O given F. So based on these values, we are going to suggest to the customer the most probable cause of the failure. Okay, so in here, the formula, as we know, this is probability of H intersection F divided by probability of F. Here, also, the probability of F intersection S divided by probability of F. And this is probability of O intersection F divided by probability of F. So we need to find the probability of F. Probability of F from the mutually exclusive events is calculated as probability of H intersection F plus probability of S intersection F plus probability of O intersection F. So we can also calculate this using the multiplication rule for probabilities. This is probability of F given H times probability of H plus probability of F given S times probability of S plus probability of F given O times probability of O. Okay, so using that expression for probability of H given F is 0.25. Probability of S given F is 0.333. Probability of O given F is 0.417. So which one is the highest value? The highest value is this one. And we will suggest that most probably the problem is from the other categories. So that's how we do. And this is the value for the denominator. And these are the values. And then we say a website dialog to diagnose the problem quickly should start with a check into the other category. So we can also do in R as follows. We can run this, probability of S, this, probability of O, probability of F given H, probability of F given S, probability of F given O, and then probability of F is 0.06 is correct. Probability of H given F is also given like this. So these are the values. And if you can see, probability of O given F is 0.4717, which is the highest value. And then we say the most probable problem is from the other category. Okay. So one last exercise is law enforcement, DNA match. This is given to you as an exercise, and please share your solutions in the comment below. In a city of 1 million people, a DNA match from a crime scene is found. The DNA test is 99.9% accurate, meaning it has a 0.1% chance of falsely matching someone innocent. If a person is randomly picked and their DNA matches the crime scene sample, what is the probability they are actually guilty? So please share your solutions in the comments below. And this is what I want to share about the Bayes theorem. And I also showed some examples of the Bayes theorem. We also discussed the multiplication in total probability rules that will help us to use Bayes theorem. Please share, like, and comment. And thank you very much. And see you in the next video.